Alright, this is the third video in chapter 13. We're looking at the properties of liquids. And instead of just focusing on liquids now, we're going to talk about how liquids can change into the other states of matter. So the physical state of matter changes. So let's first go over some of those different physical changes in state. We've already gone over a few terms this chapter already, but let's review them. Remember that if we say that a liquid evaporates, this is going from the liquid phase to the gaseous phase usually by increasing the temperature of the liquid. So it's the formation of the gas or vapor from a liquid. Remember that when we're talking about equilibrium forming in a closed container, we usually use evaporation or vaporization as our term. Alright, so evaporation is going from the liquid to the gaseous phase. The opposite of evaporation is called condensation. That's the process of going from the gas phase back down to the lower kinetic energy phase, the liquid phase. So, when do these two changes occur? Evaporation and condensation, to go from a liquid phase to a gas phase or a gas back to the liquid, both occur at the boiling point of that liquid. Alright? The boiling point. Alright, the next terms that we're going to look at are freezing and melting. I think that we know those. If you are talking about a substance freezing or solidifying, you're talking about a liquid being converted to the solid phase of matter. So freezing is going from liquid to solid. The opposite of freezing is melting, right? It's the formation of a liquid from a solid. So the solid, when it melts, is converted. So this is what a phase change diagram looks like. We need to be able to come up with one of these on our own. So let's do that. So the phase change diagram has two axes, and a y versus an x. On the y-axis we have temperature change. On the x-axis we have heat change in the system or in the substance. So remember, as you increase the heat of the system, you increase the temperature of the substance overall, and you can go through your three phases. The lowest temperatures, at the lowest amount of heat, we have the solid phase. There's a phase change or a plateau. Then we go to the liquid phase, plateau, and then we go to the gas phase. So in the system, we have three increasing our phases of matter at increasing or higher heats or temperatures. At the lowest heat or temperature, we have solid. At moderate temperatures, for any substance, we have liquid. And at the higher temperatures, we have the gas phase. Remember that the plateaus in between these three phases, as we're increasing the heat of our substance, going from gas or solid to gas, as we increase the heat, we have to go through those phase changes. The temperature at which the phase changes occurs can be extrapolated back to the x-axis. So the phase changes, we'll start with this one here first, going from solid to liquid or from liquid to solid. We know that that's either called melting if you're going from solid to liquid, so you can extrapolate back to the melting point. But if you're going from liquid to solid, the backwards process, we call that freezing. So you can also remember that the freezing point is the same thing as the melting point. Alright, so that's our first phase change. Remember, there's no change in temperature during a phase change. That line will plateau because as you increase heat energy, it goes to doing what? Breaking intermolecular forces. Okay, the second temperature change, phase change we see is from liquid to gas, or from gas to liquid, and we call that evaporation or condensation. And the temperature at which that occurs, remember, is called the boiling point. So if you extrapolate back to your y-axis once again, you can find the temperature at which that occurs. On either side of this plateau, by the way, see that dot right there and that dot right there? When you read on the line, this is a liquid at its highest temperature, and at that same temperature on this side of the plateau, we have a gas at its lowest temperature. This is the temperature of the gas at its boiling point, and this is the temperature of the liquid at its boiling point. Anything in between here is the gas and the liquid at the same time. So this is just how you read the curve, just so you know, okay? Because we're going to be looking at some problems, and you're going to have to either understand the concept in your head real easily or be able to draw a heat curve and to be able to use it. So let's look at some examples. Okay, so the examples we're going to look at relating to the heat versus temperature change diagrams and the heat curves, we're going to be calculating heat. And I know you've heard of heat as energy before. If you remember back to chapter 4, we actually calculated heat of a system. So we looked at a substance that was in one phase, like the substance of a solid, the substance of a liquid, or the substance of a gas. And we could calculate the amount of heat of that substance in that one phase using the heat equation. And we're going to use this equation again, and we're going to learn 2 more heat equations that deal with heat of a substance during a phase change. So we're going to be putting all of this together to calculate the heat changes during phase and temperature changes of a substance across multiple phases. So first of all, let's look at the old heat equation we used before when we were just talking about a substance being in one phase and not changing its matter. We said the heat of that phase, I'm going to call that Q, in one phase. This could be heat of the liquid, heat of the gas, heat of the solid, is going to equal the mass of that substance in grams times the specific heat times the change in temperature. Remember, temperature change is always T final minus temperature initial. So if we wanted to measure how much heat was required to change the temperature of a substance in one phase to the temperature of that same phase, maybe from a cold solid to a hot solid, or a cold liquid to a hot liquid, so in that one phase, this was the equation we used. Remember that specific heat was a constant, a physical constant that we could use, that we'd have to look up for each individual substance. So that constant would always be given to you. The specific heat of water is 1 calorie. Remember that? That's actually how a calorie is measured. It's the amount of heat per gram degree Celsius that it requires to change the temperature of any substance 1 degree Celsius. All right. So now we have 2 new physical constants that we're going to learn, because we're going to learn heat equations to use during a phase change. So we're going to need a new equation. Now, why are we going to need a new equation? So this is equation 1. Notice that the heat of any phase is mass times specific heat times change in temperature. What if you want to know how much heat it's going to take to change 1 gram of a solid to 1 gram of a liquid at the melting point? Remember, during a phase change, there's change in heat, Q, but there's no change in temperature, because what is all of that heat energy going to? Breaking the intermolecular forces of attraction. Okay, well, let's put this into perspective. If during a phase change there's no temperature change, your overall difference in temperature is going to be 0. You would calculate a 0 for Q. But we know that you can't get 0 for Q, or heat, because you need heat in order to do a phase change. You can't boil water on your stove without heating it, right? So you need heat in order to get a phase change. So here we're going to look at 2 new physical constants to make 2 new heat equations. The first physical constant we're going to define is the heat of fusion, and it's called H-fuse. H-fuse. This would be analogous to specific heat in this equation above. So what is heat of fusion? The heat of fusion, H-fuse, is the physical constant that measures the energy required to change 1 gram of a solid at its melting point temperature to 1 gram of a liquid. So it measures the amount of energy to change 1 gram of a solid from any substance, it'll be defined, to 1 gram of a liquid at its melting point. Okay, so it's the phase change of melting. Alright, the second one we're going to look at as our physical constant is heat of vaporization, HVAP. The heat of vaporization. This is the physical constant that's going to be used in our heat equation that defines the amount of energy required to change a gram of a liquid to its vapor or gas at its normal boiling point. So 1 gram of a liquid converted to the vapor of that liquid, the gas phase, at its boiling point. So this is the heat required to do a phase change for each gram of that substance. Alright, what we're going to do now is we're going to look at the two new heat equations, because this heat equation that we've defined earlier, I'm boxing right now, is to change the temperature of a substance without changing its phase. So next we're going to look at the phase changing heat equations. The amount of heat required to vaporize a substance, to go from the liquid, so vaporization is going from liquid to gas, or from gas to liquid, so the heat of vaporization is going to equal HVAP, the heat of vaporization constant, times the mass of the substance. Notice there's no change in temperature in this equation, because there's no change in temperature during a phase change. HVAP includes the amount of heat needed to break the intermolecular forces. Alright, so this is going from a phase change from liquid to gas or gas to liquid. We also have to have a heat equation that includes the fusion constant, so Q fuse. And this will be going from a liquid to a solid, or a solid to a liquid. So Q fuse is going to equal H fuse, the heat of fusion constant, times mass of the substance. Because the heat of fusion is per gram, you multiply it times the number of grams you have. So these are our three heat equations. Let's work some problems, and instead of just talking about this, let's learn about, from example, how we can measure how much heat will change the temperature of a substance from one phase to another phase. Okay, so here's the part of the video where you're probably going to have to finally grab your calculators, because we're going to do some calculations. We're going to calculate how much heat is needed to change the temperatures of these substances. The first one says the heat of vaporization for water is 2,259 joules per gram. Well, that's an interesting statement. You know what that is? That's just telling us the physical constant for water. I'm going to mark that up here. The heat of vaporization, HVAP, kind of like specific heat, but it's during a phase change, for water is 2,259 joules per gram. Remember, heat of vaporization is the heat required for 1 gram of liquid to be converted to 1 gram of gas. Just so you remember, that's a physical constant. The actual question here says calculate the amount of heat. So we want to calculate Q. How much heat is needed to vaporize 25 grams of water at 100 degrees Celsius? What does it mean to vaporize? Vaporize means to convert a liquid to a gas. So I want to know how much heat does it take to undergo that phase change. At 100 degrees Celsius, notice that's the boiling point of water. So at the water's boiling point, so I'm going to draw my temperature versus heat diagram real quick just to show you what we're talking about here. Here's my solid water, here's liquid water, here's gas water. We know that solid water melts at 0 degrees Celsius and it boils at 100 degrees Celsius, right? So boiling is going from liquid water at 100 degrees Celsius to gaseous water at 100 degrees Celsius. So remember, heat down here, that's Q. We want to know how much heat is this to go from the liquid phase to the gas phase at 100 degrees Celsius? How much heat is this? Notice the temperature is not changing. That's why we're not given more than one temperature, because we're at a phase change. So what is this Q here? That's really what the question's asking. What is the heat to go from the liquid at 100 to get it to go to gas at 100? All right, well, what we notice is we're in the part of the curve where there's no change in temperature. So we only have one section of our curve. What do I mean by that? So here's your heat equation. Every time, or your heat curve, actually that was really bad. Let me start all over and not go so fast. You should slow down too. Okay, so here's our heat curve, temperature, heat. The key to these equations or problems will be that every time there's a segment to this line, you'll have a heat equation. For example, here we know we have a solid. What's happening in this part of the heat diagram? Well, you're increasing heat and you're also increasing temperature. This is when you're going to use the Q phase. Heat to heat a solid from a low temperature to a high temperature equals mass times specific heat of the solid times change in temperature of the solid. So when we are on this part of the curve and it's increasing, you want to know how much heat it takes to increase the temperature, you will use that equation. It turns out that if you're in this part or this part of the diagram too, this is the liquid and this is the gas, you're going to use the same equation, liquid or gas, because you're changing the temperature as you change the heat. So the heat equation for the phase, the Q phase, we're going to use for these three segments. For the two segments that require temperature change, or no temperature changes, only heat changes, the two phase change parts of the diagram, we're going to use our phase change equations. If you're melting the compound or freezing the compound, you're going to use the H fusion times mass equation. And if you're evaporating or condensing the compound, maybe you're boiling it, you're going to use the H-evap equation times mass. Sorry, my computer won't let me write. I hate that. All right, so for every segment of the curve, and I know that's really messy, but basically for every segment of the curve, there will be an equation to use. So because we're only looking at liquid boiling to gas, we're only going to use that one equation. So the equation we're going to use is Q to boil, the amount of heat needed to boil 25 grams of my water equals the heat of vaporization, that physical constant for boiling, times mass. All right, so we want to know Q. So we're given the heat of vaporization, it's 2,259 joules per gram, and we're also given the mass of the water. It's 25.0 grams. Okay, so here's why the equation actually works. Remember, your units should always cancel out. Notice that my mass is in grams, so I've got a grams on top, and over here in my HVAP, I've got a grams on bottom. So the grams are going to cancel out. So my final unit here is going to be joules. Now I just multiply, right? 2,259 times 25.0. Let's see, that's going to be 3 significant figures because this number has 3. It's the lesser number when you multiply. So when I multiply and I have 3 significant figures, the amount of heat it's going to take to boil that 25 grams of water is just 25 times the amount of heat to boil 1 gram of water. Let's see, that calculation, this times that will give me 56,500 joules when I round it to 3 significant figures. I could also report that in kilojoules if it asked me to. Remember that there's 1,000 joules per kilojoule. So if I divide this number by 1,000, or move the decimal place over 3 places, that's 56.5 kilojoules. So always keep in mind kilo is 1,000 of something. Alright, so that was an easy problem, and I thought I'd go over all of that while we were doing it. Let's do the next problem. The next problem says The heat of fusion for water is 335 joules per gram. Let me erase everything here. So we're given the heat of fusion of water. That's H fuse. It's 335 joules per gram. It says calculate the amount of heat, so we want to once again calculate Q, needed to melt 25 grams of ice at 0 degrees Celsius. So what does it mean to melt? Let's go to our phase change diagram again, because I love these things, or our heat curve I should say. So it's temperature versus heat. We've got solid, phase change, liquid, phase change, gas. Alright, for water, we can go ahead and we can mark our physical constants. We know the boiling point of water is 100 degrees Celsius. We know the freezing point of water is 0 degrees Celsius. Here's my solid, here's my liquid, here's gas. And in between the solid, liquid, and gas, I have my phase changes. So here is melting and freezing, and here is boiling and condensing. Alright, let's look at the question again. It says, calculate the amount of heat needed to melt 25 grams of ice at 0 degrees Celsius. What does it mean to melt ice? To melt is to go from solid to liquid. So if I've got ice at 0 degrees Celsius, I'm at the top of my heat curve for water. And if I want to melt the ice, I just convert it all to liquid without changing the temperature. So we have one segment of our curve here. Notice there's no change in temperature. So I'm going to use the melting equation for heat, which is heat of fusion times mass. Alright, the heat of fusion of water was 335 joules per gram. And once again, I've got 25 grams of water, so I'm going to multiply that times 25.0 grams. Grams on bottom, grams on top. My unit left will be the joule. So I've got how many joules? 335 times 25.0. Let's see, three significant figures. I get 8,380 joules. 8,380 joules of heat needed to melt that. Can you convert that to kilojoules? Let's do the conversion. Remember good old conversions? Because you're going to need to remember all of those conversions. So remember that if you're converting, you're going to use those metric conversions we learned about in Chapter 2. Alright, so if you're converting to kilojoules from joules, you've got the joule on bottom, you've got the kilojoule on top. Remember, kilo means 100. So if you have 1 kilojoule, you have 1,000. A kilo means 1,000. So if you have 1 kilojoule, you have 1,000 joules. So the joules are on bottom, so I'm going to divide by 1,000. One thing you could do instead of getting your calculator out is if you divide by 1,000, you just move the decimal place over 3 times. So the answer here will be 8.38 kilojoules with 3 significant figures. So these are actually the same number, just reported in different metric units. Okay? So just be careful. Sometimes the question will ask you for joules, sometimes it will ask you for kilojoules. It's just stuff we've done before minor conversions. Okay, let's try a harder problem now. And by harder, I don't mean you can't do it. I just mean more complex or more steps. So, first of all, I'll just read what I've written here. If you have a heat problem and you need to calculate the amount of heat required to change the temperature of a sample, and that sample during your heat problem will contain 2 or more phases. So you'll start in one phase, you'll go to another phase, and during that process there's also a temperature change, which means you not only had a phase change, but you also heated the sample as well. You're going to need more than one heat equation. What you're going to do is you're going to use all of the heat equations individually, and you're going to sum them all together for the total heat change. We're going to learn what exactly I mean by this using an example that's kind of written out in your notes already. So this example problem says, right here, calculate the energy needed to convert 25 grams of ice at 0 degrees Celsius to steam at 100 degrees Celsius. Sorry, that got cut off there. It should be there. So let's read it again. It says, calculate the energy. Okay. Heat, remember, is a form of energy. So when it says to calculate the energy in these problems, it's asking you what the overall heat is that's needed to convert. Once we've got 25 grams of ice, and we're converting it to steam. So ice, remember, is a solid. Steam, remember, is a gas. So we're converting 25 grams of ice at 0 degrees Celsius to steam, which is gas, at 100 degrees Celsius. Before I even start solving the problem, meaning adding equations in here and there, I want to know what heat equations I'm dealing with. And I want to get a better picture of what this overall equation is going to look like. So I'm going to go over to the next page. Whenever I have heat problems, I always like to start with my heat curve. Remember, your heat curve is temperature versus heat. Okay? And we're just going to draw the three phases of matter. Obviously, since we're dealing with the terms ice and steam, we're dealing with water. So water, we know, has a solid phase of matter, ice. Then it's melted. Solid converts to liquid, liquid converts to solid. And after it's melted, we have liquid water at a higher heat, a higher temperature. And that liquid can be boiled to give us steam, or can be condensed back down to the liquid. And that will take us into our steam, or a gaseous phase of water. Alright, so here's a generic heat diagram, or a heat curve. How do I make this specific to water? On the y-axis, we're going to add in our melting and boiling points. Usually those will be given to you. You will have a properties of substances chart, or I'll give them to you in the problem. So you can look up the melting point and the boiling point of water. Here is the melting, and here is the boiling points of water. The melting point of water we know is 0 degrees Celsius. And the boiling point of water is 100 degrees Celsius. Okay, let's go back to the problem real quick. In the problem, we were given 25 grams of ice, so we started out at 0 degrees Celsius for ice. Ice is the solid form of water. And we're going to end up with steam, right? Steam is the gaseous form of water. So where is 0 degrees Celsius for ice? 0 degrees Celsius is the melting point. So notice the 0 degrees Celsius is this entire line right here. Where are we going to start? We're going to start on the ice side. So our first point, this is where we're going to start, is going to be that we have 0 degrees Celsius ice. Alright, where are we going to end? We end with 100 degrees Celsius for our steam. So 100 degrees Celsius for steam, here's our steam, and that's right at the boiling point. So are we going to start on this side of the line, or are we going to end on that side of the left side, or the right-hand side of the 100 degrees Celsius? Well, since we're steam at 100 degrees Celsius, we'll be ending on this side of the line for that temperature change. So what's going to happen here in order to get the ice to the 100 degrees Celsius steam? The plan is this. First, we have to melt the ice. First, we have to melt the ice. The second thing we have to do, the second segment of the line, is we have to heat the liquid water. That's our second segment of the line. Once we get there, every segment, remember, is a different step in a different equation. So once we got to 100 degrees Celsius for the liquid water, then we are going to boil the water to 100 degrees Celsius. So we have to convert all of that liquid water into gaseous steam at that temperature. We have to boil the water. And then we'll have all 25 grams of our water converted to 100 degrees Celsius steam. So notice there's 3 steps planned here because we have 1, 2, 3 segments of our heat curve that we're going to need to use. So first of all, let's melt the ice. Alright, we're going to plan it out. The total heat, by the way, that we'll be calculating, Q total, is going to equal the heat required to melt the ice, our first step, plus the heat required to heat the liquid once it's all been melted up to 100 degrees Celsius. And then we're going to have to boil that water to steam at 100 degrees Celsius. So we're going to do each of these individually. Q total will equal the 3 of these. So we're going to go with melting the ice first. To melt the ice, that's during a heat transition. That's the heat of fusion of water times the mass of the water. Now, we were given the heat of fusion earlier. It was 335 joules per gram. That's something you could look up because it's a physical constant for water. The heat of fusion can always be looked up for any substance. And we've got 25 grams of water. So the heat of fusion times the mass, we did this earlier actually, but I'm not going to round until the end, by the way. So this time I'm going to wait to round until the very end because I'm going to do a summation. So I have 8,375 joules to melt the ice. Okay, I'm going to put that one, that's there. Now let's calculate the amount of heat needed to change the liquid water from 0 degrees Celsius to 100 degrees Celsius, now that it's been heated. So we're going to warm that water. So the Q of the liquid, that's a certain phase, will equal the mass of the liquid times the specific heat times the change in the temperature. Alright, that's the first equation we used all the way back when. So we have 25.0 grams of our water. The specific heat of water, we're going to be using joules, so it's 4.184 joules per gram degree Celsius. And I don't have enough room to write the temperature change here. Actually, I will. Let me just stick it on the side here. And the change in temperature, it's T final, which is 100 degrees, minus T initial, which is 0 degrees, the initial cold water. So 100 minus 0 is 100.0 degrees Celsius. Okay, so once again, we should have 3 significant figures because of this number here, but we're going to go ahead and wait till the end to round. So I'm going to calculate my liquid warming heat required. It's 10,460 joules. Alright, 3 significant figures. Finally, so that will be this heat. And I'm going to go to my next page because I'm around room. The amount of heat needed to boil the water. So once we get the water to 100 degrees liquid, we need to convert it to 100 degrees gas or steam. So we need to boil that water. That's a phase change, so we're going to use our phase change equation. It'll be H vaporization to vaporize times mass. We used the heat of vaporization constant earlier, but if you needed to look it up, you could always look it up. Those constants are given. It's 2,259 joules per gram for water times the mass, which is 25.0 grams. So we've got a grams on top and bottom. The amount of heat needed to boil or evaporate the water, I get as 56,000, and I'm not going to round it yet, 475 joules. Now, if you chose to round at each step, as long as you show your work, I'm not going to be angry at you. I know what you're doing if you show your work. And your answer is going to be approximately right. It just might be off a figure here or there. But, the best practice for a chemist is to always wait till the end to round. And I think the more experience you get with math, the better you'll get at that. Okay, so that's my other equation. If you go back, we can actually get Q total here. Remember that now that we've heated the water in these 3 individual steps, we can add up the individual heats to get the total heat needed to go from ice to that steam. So it was 8,375 plus 10,460 plus 56,475. If you round that to the 3 significant figures needed, you're going to get 75,300 joules total, if you add those 3 terms together. And for the sake of time, I'm not going to show all that. If you want to report that in kilojoules, move your decimal place over 3, okay, divide by 1,000, and you'll get 75.3 kilojoules. So both of these numbers could be correct. It just depends on how someone asked you. But those are the same terms. So that's how much heat would be required to convert all that ice to steam. Go ahead and practice some other problems. There are plenty of problems in the book. We're not going to look at them all. But practice plenty of problems to understand really how to use these heat equations. Which equations you're going to use when. Every problem can be individually different depending on what temperature you start with and end with for each substance and how many equations you use. So just get very familiar with applying these after you diagram out your heat curve and you kind of know what's going on. Practice makes perfect.